Okay, so here are the measurements in millimeters of a critical dimension on a simple random sample of 16 of the more than 200 Otto engine crankshafts produced in one day. Part A. Construct and interpret a 95% confidence interval for the process mean at the time these crankshafts were produced. Okay, so we're going to break this into our four-step process. So we're going to start with our statement, and we're going to say that we are trying to estimate the true population mean critical dimension of all the engine crankshafts produced in one day at a 95% confidence level. Be sure you mention mu as your population parameter. Next, we go to our plan. And our plan is we're going to use a one sample t interval to estimate the true population mean mu. And that's going to be as long as our conditions are met. And so next, we're going to need to check our conditions. So that'll be our random condition, our 10%, and our normal large sample condition. So our random condition, we can see that a simple random sample was used. It's stated there, so that is met. Then we look at our 10% condition, and so that means that we take no more than 10% of the entire population. And so our sample size was 16, and 10 times 16 is 160. And so since it says that there's more than 200, so we can say that we took no more than 10% of the population, so that condition is met. And now our normal large sample. Now, the normal large sample says that either it has to state that the population distribution is approximately normal, which it doesn't, or that the sample size is at least 30. So neither of those are met. It doesn't state that the population distribution is approximately normal and the sample size is not at least 30. So what we need to do is then inspect a graph of the sample data. So we're going to make a graph of these 16 values and see what we get. And you can use a dot plot, histogram, or box plot. It actually doesn't matter. I like using the box plot. So in your graphing calculator, you can go to Stat, and go to Edit, and I already have the 16 values in here. They're all in list 1. And from here, I'm going to go to stat plot. So I'm going to press second, and then y equals. And just have one of your plots on. Make sure that the rest are off. So I'm going to go to plot 1. And I'm going to highlight the box plot. Now, you see there's two box plots here. There's this one and this one. The difference is that this first one's going to show you the outliers as separate values. They're going to have gaps between the outliers and the rest of the box plot. So you want to use this one because it'll show clearly when you have outliers. This one doesn't. So use this one. And it'll usually show the outliers also in like stars or something. So we're going to use the data from our list 1. And the mark doesn't matter, but use something that you can see. Then we press zoom. We go down and zoom stat. Press enter. And there's a graph for a box plot. Now, we just have to see that, oops, going back to that. We inspect our data, and as long as there's no outliers or extreme skewness, then we're good to go. It doesn't have to be perfectly symmetrical, but as long as we can say that there's no strong skewness or outliers, we're good. So we just draw a sketch of this. And you can also even trace the values. If you press trace and see what the values are, like our minimum is 223.902. Here's for Q1, our median, Q3, and max. It's usually not necessary. Make sure you draw a reasonably accurate sketch. And so there's our box plot. And again, mention this when you are completing your solution. Mention what you're doing and why you're doing it. So our box plot shows no outliers or strong skewness, so it's safe to proceed. Now we do our calculation. So this is where we're going to use our confidence interval formula. So that'll be our, x bar, our sample mean, plus minus our critical value t star times our sample standard deviation, s sub x over the square root of n. So our x bar, we can use our calculator to calculate this, and we can also calculate the sample standard deviation from our calculator. So it's already in our data, so we can go to stat and go to calc, go to one variable statistics, and type list 1, because that's where our data is, and press enter, and that'll give us all the statistics from our data. Our sample mean is 224.0019.375. And if you look, there's two values for the standard deviation. You're going to use this one because that's our sample standard deviation. The difference is that this one divides by n-1, whereas this standard deviation, which is the population standard deviation, just divides by n. So we're going to use the 0.0618. And also gives you other values in case you need them. Now the other thing we have to figure out is our t star value, and that's going to come from what our degrees of freedom will be and our confidence level. So since we're trying to estimate with 95% confidence, we're going to look for the 95% confidence level on our t-table, and our degrees of freedom will be one less than our sample size. Our degrees of freedom will be 15. So going to our table, you go to degrees of freedom of 15, and we go to the column that has 95% confidence. We're going to look at this column. So we're going to use our t-star value of 2.131. And the rest is it's pretty much just plug and chug, so it's calculation. So our formula will come up to be like this. 224 plus or minus our 2.131 times our sample standard deviation and the square root of our sample size, square root of 16. And again, just be careful that you do this correctly. These numbers work out kind of nicely because the square root of 16 is just 4. So we do 0.0618 divided by the square root of 16, which is just 4. Multiply that by 2.131. And that'll be a margin of error, so we're going to add and subtract that to 224. So plus 224, 24 minus 0.0329, 2395. So that'll give us our lower and upper bounds of our confidence interval approximately. And there we go. Now we just conclude what we figured out. So we can say that we are 95% confident that the true population mean lies in this interval. Now let's follow up on part B. So in part B, we're saying the process mean is supposed to be 224 millimeters, but it can drift away from this target during production. So does this intervals that we got from part A, the interval that we just found out, does this interval suggest that this is not the true mean? Does it suggest the process mean has drifted? So 224. So our answer is going to be no, because our interval captures 224. And so if it captures 224, that means 224 is a plausible value. So since this is a plausible value, that means 224 could be the true population mean. It doesn't have to be centered. It actually is centered, which is coincidentally, but it doesn't have to be. It could be at the edge, at the right end or left end, doesn't matter. But as long as it's within the interval, we can be pretty confident that it is the true population mean.